September 14th, 1943. Rechlin Air Base, 60 miles north of Berlin. Oberingenieur Klaus Hartmann stood in Hangar 7, staring at an engine that should not exist. Not in this condition. Not after what it had been through. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The engine was a Pratt & Whitney R2 800 double wasp. 18 cylinders arranged in 2 radial rows. Displacement 2 800 cubic inches. Rated power 2,000 horsepower. American. The engine had been recovered from a downed B-17 Flying Fortress shot down over occupied France 3 weeks earlier. The bomber had been on its 63rd combat mission when German fighters finally brought it down. Hartmann's team had disassembled the engine completely. Every cylinder, every valve, every bearing. Every component laid out on examination tables under harsh electric lights. Standard procedure for captured enemy aircraft engines. Examine them, measure tolerances, document wear patterns. Identify weaknesses. Learn what you can. Use that knowledge to improve German designs or exploit American vulnerabilities. But this engine showed something Hartmann had never seen before. Something that made no engineering sense whatsoever. The engine had logged over 200 operational hours, combat hours, high power settings, maximum stress, the kind of operation that destroys engines. German aero engines rarely survived 50 hours under similar conditions before requiring complete overhaul or replacement. This American engine had run 4 times longer and still showed minimal wear. Hartmann picked up a piston. Standard inspection. Visual examination first. Look for scoring, cracks, heat damage, any signs of degradation. The piston surface was smooth. No significant scoring, no cracks, minimal carbon buildup. He measured the piston diameter with precision calipers. Compared the measurement to factory specifications they had obtained from captured American technical manuals. The piston was within tolerance. After 200 hours, he examined the cylinder walls. Minimal wear. The crosshatch pattern from the original machining was still visible. In a German engine, after 200 hours, those cylinder walls would be scored, worn smooth, requiring replacement. This American cylinder could be reused. He checked the crankshaft. No significant wear on the bearing journals. The connecting rod bearings showed normal wear patterns, but nothing excessive. The valves were intact. The valve guides were within specification. The whole engine could have been cleaned, inspected, reassembled, and returned to service. Hartmann called over his senior metallurgist, Hauptmann Werner Steiner. Steiner had been analyzing German and Allied engine materials since 1941. He knew metal composition, heat treatment, processes, manufacturing tolerances. If anyone could explain this impossible durability, it was Steiner. Hartmann showed him the measurements, pointed out the minimal wear, asked the obvious question, how? Steiner examined the components himself. He conducted hardness tests, checked surface finishes, analyzed the metal grain structure under magnification. His conclusion was immediate and disturbing. The Americans were using superior materials and superior manufacturing processes, not incrementally better, fundamentally better. The pistons were forged aluminum alloy with a composition German industry could not replicate at scale. The cylinder barrels were steel with a nitriding treatment that created an extremely hard, wear-resistant surface. The crankshaft was forged steel, heat-treated to specifications that required precise temperature control. German factories struggled to maintain consistently, but material quality was only part of the explanation. The real difference was manufacturing precision. Hartmann measured clearances between moving parts, piston to cylinder clearance, bearing clearances, valve stem to guide clearance. Every measurement was consistent, every component manufactured to extremely tight tolerances. The Americans were achieving precision in mass production that German manufacturers could only achieve in small batch, hand-fitted production. This was not prototype quality. This was production quality. The engine had been built in a factory in Connecticut, one of thousands produced monthly. Mass-produced with precision that German aircraft engine factories, despite their skilled craftsmen and their proud engineering tradition, could not match at scale. Hartmann had spent his entire professional life in aircraft engine development. He had worked at BMW. He had consulted for Daimler-Benz. He knew German aero engine capabilities intimately. He knew what German factories could produce, what materials were available, what tolerances were achievable in mass production. German engines were excellent designs. The BMW 801 Radial, the Daimler-Benz 605 inverted V12, the Junkers Jumo 211 inverted V12. All sophisticated, powerful engines designed by talented engineers. But they all shared the same fundamental limitation. They wore out quickly under combat conditions. 50 hours was typical before major overhaul. Some engines failed sooner. Very few lasted longer. This created enormous logistical problems. Aircraft engines were complex, expensive components. Replacing them required skilled mechanics, specialized tools, and time. An aircraft grounded for engine replacement was an aircraft not flying combat missions. Multiply that across thousands of aircraft, and the operational impact was staggering. The Luftwaffe was constantly struggling with engine availability. Serviceable engines were precious. Worn engines were rebuilt when possible, but rebuilding capacity was limited. New production barely kept pace with attrition. And here was an American engine that lasted 4 times longer. The operational implications were obvious and terrifying. American bombers could fly more missions per engine. American maintenance crews spent less time replacing engines and more time keeping aircraft operational. American logistics required fewer spare engines to maintain the same number of operational aircraft. The Americans had solved an engineering problem that German industry had accepted as an unavoidable constraint. Hartmann wrote a detailed report. 14 pages. Technical specifications. Material analysis. Manufacturing observations. Operational implications. He concluded with a recommendation. German aero engine manufacturers must improve materials, tighten tolerances, and increase durability, or accept that American bombers would maintain higher operational rates than Luftwaffe fighters could sustain. The report went to the Reichsluftfahrtministerium, the Reich Aviation Ministry. It was read by senior officials. It was filed. Nothing changed. Changing engine manufacturing required retooling factories, sourcing different materials, retraining workers, and accepting lower production rates during the transition. Germany in 1943 could not afford production disruptions. The Eastern Front was consuming aircraft faster than factories could build them. Strategic bombing was destroying German industrial capacity. The Luftwaffe needed engines now, not better engines next year. So German factories continued producing engines the same way they always had. Skilled craftsmen, traditional methods, 50-hour service life, and American bombers kept coming. The bomber streams appeared over Germany with increasing frequency. Hundreds of aircraft, flying in tight formations, protected by long-range fighters, dropping thousands of tons of high explosives on German cities, factories, and transportation networks. Each bomber had 4 engines, 4 American radial engines that would run reliably for 200 hours or more. That reliability translated directly into combat capability. American bombers could fly mission after mission. Their engines did not fail. They did not require constant replacement. The maintenance burden was manageable. The operational tempo was sustainable. German fighters opposing those bombers had engines that required replacement every 50 hours. The Messerschmitt Bf 109 used a Daimler-Benz 609 engine, excellent design, 1,475 horsepower, but high-strung, temperamental, prone to overheating, quick to wear out. The Focke-Wulf E190 used a BMW 801 Radial, reliable by German standards, 1,700 horsepower, but still required overhaul at 50 hours. German pilots loved their aircraft. They praised their handling, their firepower, their performance. But they all knew the engines were fragile. Push them too hard, and they failed. Combat required pushing them hard constantly. Hartmann's report was not the first document noting American engine durability. Similar reports had been written since 1942. Captured American aircraft were examined regularly. Every examination reached the same conclusion. American engines lasted longer, much longer. The durability gap was consistent across all American engine types. Radial engines, inline engines, large engines, small engines, all showed the same superior longevity. This was not luck. This was not isolated to one manufacturer. This was systematic. The Americans had developed manufacturing capabilities that produced durable engines at scale. In December 1943, Hartmann was assigned to a special project. The Reichsluftfahrtministerium wanted a comprehensive comparison. German engines versus American engines, durability, reliability, maintenance requirements, operational availability. Everything quantified, everything documented. Build the case for why German engine production needed radical reform. Hartmann assembled a team, metallurgists, manufacturing engineers, test pilots, maintenance personnel. They had access to captured American engines and complete German production data. The project took 4 months. The findings were damning. American radial engines averaged 200 hours between overhauls under combat conditions. Some engines exceeded 300 hours. German radial engines averaged 48 hours under equivalent conditions. Some failed sooner. Very few reached 60 hours. The disparity was consistent across engine sizes and power ratings. American inline engines showed similar advantages. The Allison V1710 used in P-38 fighters regularly exceeded 150 hours. The Packard-built Rolls-Royce Merlin, used in P-51 Mustangs, exceeded 200 hours. German inline engines rarely reached 75 hours. The team analyzed why. Material quality was a factor. American steel alloys were more consistent. American aluminum alloys had better high-temperature properties. American bearing materials lasted longer under load. But materials alone did not explain the full disparity. Manufacturing precision was the critical difference. American factories achieved tighter tolerances in mass production than German factories could match. The Americans used automated machinery, precision grinding equipment, standardized quality control. Every component met specification. Every engine was built to the same standard. Interchangeable parts. Predictable performance. Reliable durability. German manufacturing relied more on skilled craftsmen, hand-fitting components, individual attention to each engine. This produced engines that could be excellent when everything went right, but consistency was lower. Component quality varied. Some engines were superb, others were merely adequate. Durability varied accordingly. The team documented the operational consequences. A Luftwaffe fighter squadron with 30 aircraft needed approximately 60 engines per month to maintain operational strength. That assumed each aircraft flew 20 hours per month and engines were replaced every 50 hours. Reality was worse because many engines failed before reaching 50 hours. An equivalent American fighter squadron needed approximately 15 engines per month. Same 30 aircraft. Same 20 flight hours per aircraft per month. But engines lasted 200 hours. The logistical burden was 4 times lower. Fewer spare engines required. Less warehouse space. Fewer transport vehicles. Fewer mechanics dedicated to engine replacement. More aircraft available for combat operations at any given time. The German system was grinding itself down through sheer logistical friction. Hartmann's final report was 73 pages. Charts, tables, photographs, technical specifications, operational analyses, recommendations. The conclusion was stark. German aero engine manufacturing must achieve American standards of precision and durability, or the Luftwaffe would lose the war of attrition. Not because German pilots lacked skill, not because German tactics were inferior, but because German engines wore out faster than they could be replaced, and American engines did not. The report was delivered to Reichsmarschall Hermann Göring in May 1944. Göring read it. He called a meeting with senior Luftwaffe staff and representatives from BMW, Daimler-Benz, and Junkers. The engine manufacturers explained the challenges. Retooling would reduce production for 6 to 12 months. Germany could not afford that disruption. New materials were scarce. Alloying elements were in short supply. Chromium, nickel, molybdenum, all imported or captured from occupied territories. Supplies were uncertain. Precision machinery required for tighter tolerances was not available in sufficient quantities. Much of it was imported from Switzerland. Swiss exports to Germany were declining due to Allied pressure. Even if Germany could retool factories and source materials, training workers to new standards would take time. Skilled workers were being conscripted into combat units. Factories were filling positions with forced labor. Foreign workers, prisoners, people with no experience and no investment in quality. Achieving precision manufacturing under those conditions was nearly impossible. Göring understood the situation. He authorized funding for incremental improvements, better materials, where available, improved quality control, where feasible, but no radical transformation. The Luftwaffe would continue operating with engines that wore out 4 times faster than American engines. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. By mid-1944, the consequences were visible across the Luftwaffe. Fighter units were chronically short of serviceable aircraft. Not because airframes were destroyed, airframes could be repaired, but because engines were worn out and replacements were not available. Bombers sat grounded, waiting for engines. Transport aircraft could not fly supply missions. Training aircraft could not train new pilots. The entire aviation system was constrained by engine availability, and American bombers kept coming, wave after wave. Day after day, their engines running smoothly, 200 hours between overhauls, sometimes more. German mechanics working on captured American aircraft marveled at the engineering. They saw pistons that could be reused, cylinder walls that did not need replacement, crankshafts that were not scored. They compared American components to German components with equivalent hours, and the difference was obvious. German parts were worn, damaged, requires replacement. American parts were serviceable, could be reused, could be rebuilt. One German mechanic famously said, "The Americans build engines as if they expect them to last forever. We build engines as if we expect them to fail tomorrow." Both approaches were self-fulfilling. The engineering disparity was not limited to durability. It extended to every aspect of engine design and manufacturing philosophy. American engines were designed for ease of maintenance, modular construction, Standardized components. Mechanics could remove an engine from an aircraft, install a replacement, and have the aircraft flying again in hours. The removed engine went to a depot for complete overhaul. Specialized facilities, automated equipment, assembly line rebuilding. Engines were disassembled, cleaned, inspected, worn parts replaced, reassembled, tested, and returned to inventory. The system was efficient, predictable, sustainable. German engine maintenance was more complicated. Engines were often repaired in the field, skilled mechanics, working with limited tools, improvising solutions, hand-fitting replacement parts. Because standardization was inconsistent, the work took longer, required more skill, produced less predictable results. Some field repairs were excellent, others barely functional. Depot overhauls existed, but capacity was limited. Bombed facilities, labor shortages, material shortages. The overhaul system could not keep pace with demand. The philosophical difference ran deeper than mere maintenance procedures. American military doctrine treated engines as expendable components within a larger system. An engine was not a precious artifact to be nursed along indefinitely. It was a time-limited asset with a predictable service life. When that life expired, the engine was replaced. No sentimentality, no attachment, just swap it out and move on. This mindset required abundant production capacity, required logistics systems capable of moving replacement engines wherever needed, required confidence that the supply would never run dry. America had all of these things. German doctrine reflected different constraints. Engines were precious because they were scarce. Each engine represented hundreds of hours of skilled labor, represented materials that were increasingly difficult to obtain, represented manufacturing capacity that was being bombed into rubble. You did not casually discard a German engine. You repaired it. You rebuilt it. You coaxed every possible hour of operation from it before finally admitting it was beyond salvation. This approach made sense, given German resource limitations, but it was inherently less efficient than the American approach. In July 1944, Hartmann visited a Jagdgeschwader fighter wing base in France. He was conducting field research, observing maintenance operations, talking to mechanics and pilots, understanding operational realities beyond laboratory analysis. The base had 30 Focke-Wulf W190 fighters assigned. Only 18 were operational. The others were grounded, waiting for engines. The wing's maintenance officer, a Hauptmann named Joseph Klein, showed Hartmann the engine storage area. 6 engines awaiting installation, all rebuilt units, all with unknown service history. Some pulled from crashed aircraft and hastily repaired. Others returned from depot overhaul with no documentation of what work had been performed. Klein explained that he never knew if a replacement engine would last 10 hours or 50 hours. Some failed almost immediately. Bearing failures, cylinder failures, cooling problems. Others ran adequately for a while before developing issues. Planning maintenance was impossible because engine reliability was unpredictable. He kept aircraft grounded as spares, cannibalized parts from them to keep other aircraft flying. The operational readiness rate hovered around 60%. 40% of assigned aircraft were always non-operational, waiting for parts, waiting for engines, waiting for mechanics to finish work on other aircraft. Klein walked Hartmann through his maintenance logs. The documentation told a story of constant crisis management. One aircraft had received 3 different engines in 2 months. The first lasted 8 hours before a catastrophic bearing failure. The second lasted 23 hours before losing compression in multiple cylinders. The third was currently installed, but already showing oil consumption problems after just 12 hours. Another aircraft had been grounded for 6 weeks, waiting for a replacement crankshaft. The part finally arrived but was incorrectly machined, did not fit, had to be hand-modified by Klein's most skilled mechanic, took another week. The aircraft finally returned to service with an engine that Klein did not trust but had no choice but to use. Hartmann asked about American aircraft they had shot down. Had Klein's men examined American engines? Klein nodded. He walked Hartmann to a storage shed. Inside was a Pratt & Whitney Rhone 830, twin Wasp recovered from a downed P-47 Thunderbolt. The engine had been hit by cannon fire. 2 cylinders destroyed. But the rest of the engine was intact. Klein's mechanics had examined it. They found the logbook in the aircraft wreckage. The engine had 173 hours. The mechanics measured the undamaged cylinders. Minimal wear. They examined the crankshaft. Perfect condition. They checked the bearings. Like new. Klein said his men were demoralized by it. They worked 12-hour shifts keeping German engines running, replacing worn parts, fighting chronic failures. And here was an enemy engine with 3 times the hours showing less wear than German engines with 50 hours. How were they supposed to compete against that? Hartmann had no answer. He knew the engineering reasons. Superior materials, tighter tolerances, better manufacturing. But Klein's question was operational, not technical. How do you maintain combat effectiveness when your engines fail 4 times faster than the enemy's? One of Klein's mechanics, a Feldwebel named Otto Becker, had been working on aircraft engines since 1938. He had maintained engines on Stukas during the Battle of Britain, had kept Messerschmitts flying on the Eastern Front, had seen the steady decline in engine quality and availability over 5 years of war. Becker told Hartmann that early war engines were better. The WWII engines delivered in 1940 were well made, consistent quality, predictable performance. By 1944, the same engine model was noticeably inferior. Rougher castings, looser tolerances, inferior materials. He could feel the difference. Engines vibrated more, ran hotter, wore out faster. Becker had kept a personal record. In 1940, the average BMW 801 in his unit lasted 62 hours before requiring major work. In 1944, the average was 38 hours. Same engine design. Same operational conditions. 39% reduction in durability over 4 years. The decline reflected the degradation of German manufacturing capability. Skilled workers conscripted. Materials rationed. Factories bombed. Quality control abandoned in favor of meeting production quotas. The engines rolling off assembly lines in 1944 were shadows of what had been produced in 1940. The answer was, you could not. Not indefinitely. The attrition math was inexorable. Every hour of combat flying wore down German engines toward failure. Every hour of American combat flying brought American engines closer to routine maintenance intervals they would easily survive. Over time, the German engine inventory depleted faster than it could be replenished. American engine inventory remained stable. More engines arrived from factories than were consumed by operations. The balance shifted steadily against Germany. Hartmann returned to Rechlin and wrote another report. This one focused on field maintenance realities. He documented the 60% operational readiness rate, the unpredictable engine reliability, the cannibalization practices, the demoralized maintenance crews. He contrasted this with captured American maintenance manuals that specified standardized procedures, predictable maintenance intervals, and interchangeable parts. The American system was designed to be operated by adequately trained personnel, following clear instructions. The German system required highly skilled craftsmen improvising solutions. The American maintenance manuals fascinated Hartmann. They were comprehensive, detailed, written in clear, simple language. Every procedure broken down into numbered steps. Every specification precisely stated. Every tool requirement listed. The manuals assumed the mechanic was competent but not necessarily experienced with that specific engine. They provided enough information that a mechanic who had never seen that engine before could successfully perform maintenance following the instructions. The manuals were designed for an industrial workforce. Standardized training, interchangeable personnel, scalable operations. German maintenance documentation was different, less detailed, assumed higher skill levels. Assumed the mechanic already understood German engine design philosophy and construction methods. The documentation provided specifications and tolerances, but expected the mechanic to determine appropriate procedures based on experience and judgment. This worked well with highly skilled personnel, worked poorly with the increasingly inexperienced mechanics filling positions as veterans were reassigned to combat units or were killed. The American approach scaled: train more mechanics, distribute more manuals, build more depot facilities. The system expanded to match the size of the Air Force. The German approach did not scale. Skilled craftsmen took years to train, could not be rapidly expanded, were increasingly conscripted into combat units. The maintenance system was contracting, even as the Luftwaffe needed more maintenance capacity. By August 1944, Germany was losing the maintenance war as decisively as it was losing the production war. American strategic bombing accelerated the decline. Factories producing aircraft engines were priority targets. BMW's main plant in Munich was bombed repeatedly. Daimler-Benz facilities in Stuttgart suffered heavy damage. Juncker's plants in Dessau were hit hard. Production declined sharply. New engines became scarce. Luftwaffe units made do with whatever they had. Engines were run far beyond recommended limits. 50 hours became 70 hours, became 100 hours. Not because the engines could handle it, but because no replacements existed. Catastrophic failures increased. Aircraft lost not to enemy action but to engine failure. The psychological toll on pilots was significant. They were being asked to fly aircraft with engines they knew were unreliable. Every takeoff carried the uncertainty of whether the engine would keep running. Every combat engagement meant pushing engines that were already operating beyond their designed limits. Engine failures during takeoff were often fatal. No altitude to recover, no time to react. Engine failures during combat meant vulnerability. Loss of power meant loss of speed and maneuverability. Easy targets for enemy fighters. Pilots noticed. A Messerschmitt Bf 109 pilot named Lieutenant Hans Weber kept a diary. His entries from late 1944 documented increasing anxiety about engine reliability. He wrote about taking off never quite certain the engine would keep running. He described forced landings after engine failures. He mentioned friends killed when engines quit at low altitude during combat. He contrasted this with his observations of American aircraft. He wrote, "I have shot at B-17 engines and watched them absorb hits that would destroy our engines completely, yet they continue running. One bomber I attacked had an engine on fire, completely engulfed in flames, and it kept running long enough for the pilot to reach friendly territory. Our engines quit if you look at them wrong. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this." Weber's observations were accurate. American engines were not just more durable during normal operation, they were more robust under damage, radial engines particularly. The air-cooled radial configuration meant that losing one or two cylinders did not always cause complete engine failure. The remaining cylinders could keep running. Power was reduced but not eliminated. Aircraft could limp home. Inline liquid-cooled engines were more vulnerable because cooling system damage caused immediate overheating. But even American inline engines showed remarkable resilience. Redundant systems, robust construction, damage tolerance built into the design. The Radial engine's inherent damage tolerance came from its distributed architecture. 18 cylinders arranged in 2 rows meant that losing 2 cylinders reduced power by approximately 11%. Unpleasant but manageable. The engine remained balanced enough to continue running. Oil circulation could be maintained. Cooling air still reached remaining cylinders. The pilot had options, could attempt to return to base, could look for emergency landing sites, was not immediately forced down. German inline engines had no such tolerance. The Daimler-Benz 609 had 12 cylinders arranged in an inverted V configuration. Liquid cooling meant that damage to the cooling system anywhere caused the entire engine to overheat within minutes. A single coolant line hit by a bullet meant inevitable engine failure. The pilot had perhaps 2 or 3 minutes before seizure, often insufficient time to reach friendly territory. German pilots learned to disengage immediately when they took cooling system hits. No point continuing. Combat with a dying engine. German engines were less forgiving. Cooling system damage meant immediate shutdown. Lubrication problems caused rapid failure. Combat damage that American engines might survive often killed German engines instantly. This affected pilot psychology. German pilots flew knowing their engines were fragile. Any hit near the engine meant potential catastrophic failure. They flew conservatively, avoided prolonged combat, disengaged when damage seemed likely. American pilots flew with more confidence. Engine failures were rare. Combat damage was often survivable. They pressed attacks harder, stayed in combat longer. The psychological advantage compounded the technical advantage. In October 1944, Hartmann was summoned to a meeting at Luftwaffe headquarters. Senior staff wanted his assessment. How long could the Luftwaffe maintain operations given current engine attrition rates? Hartmann presented his analysis. Current engine production was approximately 2,000 units per month across all types. Current engine attrition was approximately 3,000 units per month. Combat losses, wear-outs, catastrophic failures. The deficit was 1,000 engines monthly. The Luftwaffe was drawing down accumulated inventory. That inventory would be exhausted by March 1945. After that, operational strength would decline rapidly. Units would be grounded. Not from lack of airframes or pilots or fuel, though all were also constrained, but from lack of engines. By summer 1945, the Luftwaffe would be largely non-operational. A staff officer asked if increased production could close the gap. Hartmann said no. Factories were already operating at maximum capacity. Many were damaged. Worker productivity was declining. Material shortages were worsening. Raw material supplies were uncertain. Allied bombing was intensifying. Production would decline, not increase. Another officer asked about reducing attrition. Could engines be operated more conservatively, less combat flying, lower power settings? Hartmann explained that the enemy set the operational tempo. American bombers attacked daily. German fighters had to respond or surrender air superiority. Combat required maximum power, full throttle, emergency boost. High-stress operation that burned through engine life rapidly. You could not fight a war at cruise settings. The Luftwaffe was trapped. It needed engines to fight. Fighting destroyed engines. Replacement engines were not available. The system was collapsing under its own logic. The meeting ended without solutions. There were no solutions. The engine crisis was a symptom of Germany's larger industrial collapse. No tactical adjustment could overcome strategic resource exhaustion. The numbers Hartmann presented were actually optimistic. He had calculated attrition based on historical averages, but engine quality was declining. Engines were failing faster than historical rates predicted. The 3,000-unit monthly attrition figure would likely increase to 3,500 or 4,000 as engine quality continued degrading. The crisis would arrive sooner than March, probably by January or February. The Luftwaffe had perhaps 3 months of viable operations remaining. By November 1944, American bombers were flying with near impunity over Germany. Luftwaffe fighter opposition was declining, not because pilots lacked courage or skill, but because serviceable aircraft were scarce. Many fighter units reported fewer than 10 operational aircraft out of 30 assigned. The rest grounded. No engines, no spare parts, no fuel. The few aircraft that did fly faced overwhelming odds. Hundreds of American bombers, hundreds of American escort fighters, all with reliable engines, all supported by logistics systems that kept them operational. German pilots flew knowing they were outnumbered 10-1 or 20-1. They attacked anyway, did what damage they could. Many did not return. Hartmann visited frontline units throughout late 1944. He documented conditions, talked to pilots, examined aircraft, observed maintenance operations. Everywhere he found the same situation: chronic equipment shortages, exhausted personnel, improvised repairs, engines run far beyond safe limits, aircraft barely flyable, morale declining. Not from cowardice, but from the knowledge that they were fighting an enemy they could not defeat. The Americans had too much of everything: too many aircraft, too many engines, too many spare parts, too much fuel, too many trained personnel. The disparity was overwhelming. One fighter pilot, a veteran with over 300 combat missions, told Hartmann something that summarized the entire situation. He said, "I can beat any American pilot in a fair fight. My aircraft is excellent when it works. My training is superior. My experience is extensive. But I never get a fair fight. My engine quits. My fuel runs out. My ammunition is gone. And there are always more Americans. They just keep coming. They never run out of anything." The pilot was shot down 2 weeks later. Engine failure during combat. He survived. His aircraft did not. This pilot's experience was typical. German fighter pilots in late 1944 were among the most experienced combat aviators in the world. Many had hundreds of missions. Some had over 1,000 hours of combat time. They had survived years of brutal fighting on multiple fronts. They knew every tactic, every maneuver, every trick of aerial combat, and none of it mattered. Their engines failed. Their ammunition ran out. Their fuel was exhausted. The Americans just kept coming with fresh aircraft, full fuel tanks, and reliable engines. In December 1944, Hartmann wrote his final comprehensive report on German versus American engine technology, 81 pages. Everything he had learned over 2 years of analysis: the material science, the manufacturing precision, the design philosophy, the maintenance systems, the operational consequences, the strategic implications. He concluded that Germany had lost the engine war completely. American engines were superior in every measurable category: durability, reliability, power output, damage tolerance, maintainability, producibility. The gap was not closable with available German resources and remaining time. He recommended that Germany focus remaining engine production capacity on simplest, most robust designs. Abandon development of complex high-performance engines. Accept that German engines would be inferior. Optimize for quantity over quality. Build simple engines that could be manufactured quickly with available materials and unskilled labor. Engines that might only last 30 hours but could be produced in larger numbers. His recommendation was not adopted. Engine manufacturers continued building the same designs: complex, high performance, difficult to manufacture, quick to wear out. Production continued, declining. The resistance to Hartmann's recommendations came from multiple sources. Engine manufacturers had invested decades developing their designs. They had institutional pride. They believed their engines were fundamentally sound and that quality problems were temporary manufacturing issues that could be resolved. Senior Luftwaffe leadership did not want to admit that German engineering was inferior, did not want to accept that American mass production had defeated German craftsmanship. The truth was too psychologically difficult to acknowledge. The final months of the war confirmed every prediction in Hartmann's reports. The Luftwaffe essentially ceased offensive operations by February 1945. Defensive operations became sporadic. By April, organized resistance collapsed, not from lack of will, but from lack of capability. The aircraft sat grounded, the engines were dead, no replacements existed. American bombers flew unmolested, thousands of sorties daily, meeting no opposition, destroying what remained of German industry, transportation, and military infrastructure. The engine shortage that Hartmann had documented and warned about had become terminal. After Germany surrendered in May 1945, American intelligence teams interrogated German engineers and examined German facilities. They found Hartmann's reports. They interviewed him extensively. He explained German engine development, manufacturing limitations, material shortages, everything. American engineers were surprised not by German technical incompetence, but by how close German designs had come to matching American performance, despite severe resource constraints. German engineers knew what needed to be done. They understood materials science. They comprehended precision manufacturing. They simply lacked the industrial capacity and raw materials to implement their knowledge at scale. One American engineer who interviewed Hartmann noted that German aero engines represented brilliant engineering compromised by inadequate manufacturing. The designs were sophisticated, often more advanced than equivalent American designs, but German factories could not build them to specification consistently. Material substitutions were common. Inferior alloys replaced specified materials. Tolerances were loosened to increase production speed. Quality control was inadequate. The result was engines that performed well when newly manufactured but degraded rapidly under operational stress. German engineers designed engines that could theoretically last 200 hours. German factories built engines that actually lasted 50 hours. The American approach was philosophically different. American engineers designed engines that were deliberately overbuilt, heavier than theoretically necessary, wider safety margins, conservative stress levels, simpler designs that were easier to manufacture. The design philosophy accepted reduced maximum performance in exchange for reliability and producibility. An American engine might produce 10% less power per pound than a German engine, but it would produce that power reliably for 4 times as long, and American factories could build 10 times as many. The operational advantage was decisive. Hartmann later reflected on the lessons. He concluded that engineering excellence without manufacturing capacity was militarily useless. Germany had excellent engineers, world-class designers, sophisticated theories, advanced concepts, but it lacked the industrial infrastructure to translate designs into reliable mass-produced hardware. America had adequate engineers, not necessarily superior individually, but supported by industrial infrastructure that could manufacture precision components at scale. Quality was built into the manufacturing process through automation, standardization, and quality control systems. The result was superior operational hardware despite arguably less sophisticated design. The engine durability disparity symbolized larger differences between German and American approaches to industrial warfare. Germany emphasized individual excellence, skilled craftsmen, hand-fitted components, small batch production. This produced outstanding results in limited quantities, but it did not scale. America emphasized systematic excellence, automated processes, interchangeable parts, mass production. This produced adequate results in unlimited quantities, which scaled indefinitely. In a long war, the American approach won, not because individual American products were necessarily superior, but because American industry could produce vastly more products that were adequately reliable. The Pratt & Whitney NATO 800 double WASP that Hartmann examined in September 1943 represented this philosophy perfectly. It was not the most powerful engine of its size, not the lightest, not the most fuel-efficient, but it was reliable, maintainable, and producible at scale. American factories built over 125,000 Radial engines during the war, all built to consistent specifications, all achieving similar durability, all supported by standardized spare parts and maintenance procedures. This was industrial power applied systematically to military requirements. Germany could not match it. German veterans who examined American equipment after the war consistently expressed similar observations. They recognized American technical competence. They acknowledged American engineering quality. But what truly impressed them was the sheer abundance, the endless quantities, the unlimited spare parts, the redundant systems, the casual wastefulness enabled by overwhelming production capacity. A German mechanic might spend days fabricating a replacement component because no spare was available. An American mechanic simply requisitioned a new part from supply. It arrived within days. The aircraft was repaired quickly. Back in service. The operational tempo difference was staggering. One German engine mechanic captured in 1945 told his American interrogators that he finally understood why Germany lost. He said it was not tactics or courage or even technology in the abstract. It was industry. America could build faster than Germany could destroy. American engines lasted 4 times longer than German engines. American factories produced 10 times more engines than German factories. The mathematical result was inevitable. Germany would run out of engines long before America did. When engines were gone, aircraft were grounded. When aircraft were grounded, the war was lost. Everything else, all the battles and campaigns and strategic maneuvers, was detail. The engine war determined the outcome. Hartmann survived the war. He was never prosecuted. He had been a civilian engineer, not a military officer. His work had been technical analysis, not operational command. American and British intelligence valued his knowledge. They interviewed him extensively. He provided detailed information about German engine development, manufacturing capabilities, and technical limitations. Much of what Western intelligence knew about late-war German aviation came from Hartmann's reports and post-war testimony. He later worked in West Germany's aircraft industry. He consulted on engine design. He taught engineering. He lived until 1978. In interviews late in life, Hartmann consistently said the same thing. Germany lost World War II in the factories, not on the battlefields. The Wehrmacht fought brilliantly with inadequate resources. German soldiers were brave. German officers were skilled. German equipment was often sophisticated. But none of it mattered. America's industrial capacity was simply too overwhelming. The engine durability disparity was just one example among thousands. American trucks lasted longer. American radios were more reliable. American rations were more nutritious. American uniforms were better made. American medical supplies were more abundant. Every single category showed American advantage. Accumulated across entire armed forces, the disparity was insurmountable. The 200-hour American engine versus the 50-hour German engine represented this reality in concentrated form. 4 times the durability meant 1/4 the logistical burden, meant aircraft availability rates 4 times higher, meant combat capability sustained 4 times longer, meant strategic advantages that no amount of tactical brilliance could overcome. German pilots might be more experienced. German tactics might be superior. German aircraft might have better performance. But if German aircraft were grounded waiting for engines while American aircraft flew continuous missions, experience and tactics and performance became irrelevant. Wars are won by forces that can fight continuously, not by forces with superior capabilities that cannot be sustained. The story of German engineers discovering American engine durability is not a story of German incompetence. German engineers were highly competent. They understood the problems. They identified the solutions. They wrote detailed reports explaining what needed to change. But competence without resources is insufficient. Germany lacked the raw materials, the precision machinery, the skilled labor, and the time necessary to match American manufacturing capability. By 1943, when Hartmann first examined that Pratt & Whitney double wasp, the outcome was already determined. The engine told the story. 200 hours versus 50 hours. America would win. Germany would lose. Everything else was just working out the details. Up next, you've got 2 more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to like, subscribe, and turn on the notification bell so you don't miss any upload from us.